Меня зовут Volker, я работаю в SAP. Обычно я расскажу несколько слов, что мы сделаем и почему и как, но насколько сегодня весь доклад про SAP JVM можем сразу начинать. Если есть какие-то вопросы, можете сразу спросить на любой язык, но доклад буду делать по-английски. Извините. Вот, SAP JVM. Что это SAP JVM? Это... по-английски, it's a certified Java virtual machine, and we support Java 4 to 8, and we are working on Java 9 now. It has an outstanding platform support. We will see it on the next slide. We have 15 platforms which we support. We have added a lot of supportability features and monitoring, debugging, profiling, and I will show some of them. And I will also speak about the implementation of some of these features, so I hope this talk will be also interesting for people who are interested in real internals. I will also compare some of the implementations, how they can be done in OpenJDK and how we have solved these problems. We are a team, or a quite small team I would say, of about 20 developers located in Walldorf, the SAP headquarters in Germany. And we are developing the SAP JVM since 10 years. We started out with Java 5, did 6, 7, and then may sound a little strange, after we finished Java 7 we did Java 4, 1.4, because a lot of customers who were on Java 1.4 run out of customer support from the platform vendors like HP, IBM, also Oracle or Sun, and they asked us to also support Java 1.4, so we did the late port of Java 1.4. So SAP JVM is not a completely new VM. It's based on the Sun or Hotspot, Oracle, and we've licensed the code as commercial licensees. It's a fully certified, and we also can name it Java. We are also Java trademark licensees. And what is maybe special about SAP JVM is that we do the hotspot. We call it Hotspot Extreme. It's like, maybe some of you remember Hotspot Express. It was the time when Sun for a long time did not release new Java version 7. So in order to bring new features into Java 6, they only updated the hotspot, because this was possible without the specification changes. So we like that model, and we are currently using the same VM, so same hotspot, the newest one, for all our Java versions. So we have the hotspot from Java 8, we also use it for Java 1.4, so actually we have the fastest Java 1.4 in the universe. Also many people won't care maybe. Okay, so this is our platform support. So we support Windows on x86 and Itanium, macOS, so we support all the platforms which are supported by Oracle, plus HP on PRISC and Itanium, AIX on PowerPC, System I on PowerPC, and Linux on all architectures except PRISC. Okay, so usually when I tell somebody that SAP is doing own VM, the first question is, but why are you doing it? So one problem is that Java, it's write once, run anywhere, but in reality there are some little nits which don't really are platform independent. So it just starts with command line parameters, but also with behavior like different garbage collection algorithms, different JITs, and then also all the tooling support, or logging, tracing. It's all different across the different platforms and different vendors. So especially for a company like SAP, which has a lot of products which run on Java on different platforms, this is a huge cost factor. So we decided to do our own SAP JVM, which is really the same. It offers the same features and tools on all the platforms. Also things like XML parsers, well, nowadays it's not so much a problem anymore, but a few years ago every VM vendor had its own XML implementation, and they weren't really compatible. Also security libraries are usually different across different VM versions, and so on. Also we wanted to be independent of other VM vendors, so we don't have to align with their support timeframes. So we are doing very long support. I told you we did Java 1.4 just a few years ago, and we will still support it the next 10 years at least. So we have really very long time frames, and if somebody wants to buy support from Oracle for 1.4 now, it's really expensive. So better do it yourself. Yes, and of course it's very convenient if you can integrate the Java version together with your application, so the customers aren't required to download the VM from a different vendor. So this is just some of the programs of the applications which run on our JVM. So in the beginning we had just the Java EE server and application server, but since SAP also acquired a lot of companies in the last years like Sybase, SuccessFactors, Hybris, and all of these companies do a lot of Java, we have now a lot of internal customers, which is very good for us, because at the time when Oracle acquired Sun, some people thought that SAP won't do Java anymore, but now it has changed, and I hope we will still do it for some years. So maybe you know that SAP is also engaged in the OpenJDK since some years, and actually we contributed the PowerPC and AA export to OpenJDK. So the licensing model we are using here is quite complicated, but I think it's a good model for companies to collaborate in an open source project. So we are still commercial licensees of Oracle, and we ship a commercial Java virtual machine. But in the same time, we contribute, for example, our PowerPC port to the OpenJDK project. For this, you have to sign Oracle contribution agreement, which is a copyright sharing agreement. And over the OpenJDK, we get the code we contributed back as commercial source code. Of course, that's not necessary because we have it already. But this way, we can also get contributions from other companies like Red Hat, Google, or IBM, which do improve our PowerPC port, for example, or Google did a PowerPC Little Endian port in the OpenJDK, and we can then get these improvements from other companies through Oracle back as commercial, under a commercial license. And I can tell you from my own experience, it's very hard if you want to do mutual contracts with other companies to work on a project. So we tried that, and we didn't succeed, but through one open source project like OpenJDK, it's very easy because every company has just to agree with the licensing agreements of one project, and then everybody can share the code through this open source project. So this is how we are doing it. So yeah, I already told you what our main contributions to OpenJDK have been the PowerPC and the export. Meanwhile, we have one project lead, 2 reviewers, 1 committer, and 3 authors. So I think SAP is one of the biggest external contributors. So before I start to show you some of our supportability features, I just wanted to show you a picture. You don't have really you don't have to read all this here. I just want to show this is our test matrix of the 90 tests. So on the rows, every row is a platform. So it starts with NTA MG64, NTA Tanium, NTA Intel, and it goes down till Darwin, so macOS on the left side. And here we have all the test switches we are running, like some basic tests, JIT tests, debugging tests. We also run JCK tests, benchmarks like JBB, and things like that. A lot of test suites. So each test suite may be in fact thousands of tests, and every circle here is a VM version. So that's for example, let's take here AS400, Java 4, 5, 6, 7, 8. This is the debug version. This is the opt version. So we build debug and opt versions, and we test both of them. And if it's green, it's good, like with traffic lights. And if you have a red traffic light, it means that you have a problem. And if you click on it, you see Java 4 says it has 392 tests, 2 failed, 2 crashed. Java 5 the same, SAP JVM 6, 7, and 8, there's everything okay. So people can then comment and look at the tests and...
Okay. Volker, how many rectangles do you have in this matrix?
I haven't counted.
Okay.
And yeah, this is our development code line. And we have the same picture for our release code line, our consolidation code line, and our integration code line. So We have an integration code line for Java 9, for example, which we are working on now. And of course, release and consolidation for the releases which we do. So it's actually 4 times this one. And another dimension is we also do performance tests, and it's the same matrix actually. We run like basic benchmarks starting from JVM 98, spec JVB and things like that, Da Capo and so on. And I just wanted to show you, I don't want to do any performance comparison in this talk. So this is actually, just to give you an idea, this is the comparison of the standard, we still name it Sun Hotspot, but it's Oracle Hotspot VM. It's 100%, and SAP JVM, the green one is with the standard settings, it's like between 97 and 99%. This is because of the various supportability features which we have, and the various traces and so on, which we all switch on by default. We take it as a fact that we are a little slower. So for us, it's like to be slower, like 3-4%. Actually, 3% is the border for us. We say if you're 3% slower, that's no problem. That's fine. If you have all these features switched on. So this is our goal, and we compare the benchmarks with the vendor VMs on all platforms. But of course, on the Oracle platforms, the comparison is the best one because it's the same source code from which we started. Okay, so now supportability features. This is just a brief overview. I will show you some of them live later on. So we have a lot of additional information. For example, in thread dumps, we have CPU, memory, I/O information. I think I will show you this better live. I will sit down now. Okay, and we have a tool called JVM. It's I think a little similar to JCommand or Java Flight Recorder, and this is available as command line tool and graphical user interface tool, which attaches it actually doesn't really attach it. It communicates with the virtual machine over a so-called monitoring board, which is the shared memory region, and communicates. It's loosely coupled with the VMs which are running on the local host, but you can also install a proxy to monitor and communicate with VMs on remote hosts. Okay, so let's start with the demo. So I have started 2 pet stores. This is like a very basic a Spring application which is deployed in Tomcat server, and we will take this example to demonstrate various features. So on port 8081 we are running with OpenJDK, and on port on localhost 8080 we are running with SAP JVM. So if I start now our SAP JVM monitoring tool, I will see you will see that we will see all the VMs which are running here. So I also have Eclipse running and so on, but actually this one is the VM which is running the pet store. You can see it here in the VM arguments. It's running Tomcat 7. And now we have all the features we can print. This means this output will appear right in this tool here. And actually all of this information can also be dumped, so it appears on the standard output of the running Java process. So this may be useful, for example, when you are taking traces in customer systems. Sometimes we can only attach with SSH, and you only have a command line, and then it's good to dump the results in the log files of the J2E server, for example, and then grab them from there. So I have taken a thread dump now, and here I can show you what I meant with the extended stack trace information. So you see we have, for example, we have all the time, the elapsed time, the CPU time consumed by each thread. We have the memory allocated by the thread. We have the network I/O, file descriptors, sockets, all kind of information which is logged together with the thread. And this is a very small font, I know, but the tool doesn't allow to make a bigger font, unfortunately. And each information also has in brackets so-called reset information. In this example, it's the same information, but we have some proprietary APIs which allow, for example, our application server to reset the memory counters of the thread or the I/O counters and so on. So this is very convenient, for example, for application servers to track how much a single request used of memory or CPU, because usually you have a thread pool, and the thread pool takes one request after another, and usually you want to know how much was consumed by one request. So the application server usually resets this after each request, so when somebody takes a thread dump like this, he can see that.
Does it include native memory? Or there is no native memory information?
I'm not sure if it's included here, but we have it. We have here special memory statistics. So this is comparable to the native memory tracking, which appeared in Hotspot recently, and it shows all the native memory allocation, and actually not only the memory allocations from the hotspot like NMT, but also the memory allocations in the class library. So for example, you see the zlib used most of the memory. And you see here how many memory it's using right now, how many allocations have been done, the peak size, so how much memory was used, what was the biggest usage of this call site, and at which allocate, and how many which allocation was this peak allocation, and how many times it was invoked. And our memory tracking is working a little bit different, like NMT. If you're familiar with NMT, it works by prepending some headers to each allocation, which stores the allocation site and some information. The problem with this approach is that it doesn't work well with libraries which allocate memory themselves, which you can't intercept, because sometimes you call system functions like string functions are usually a good example. They allocate memory themselves, and you get these pointers, and later on you don't know how to free them. You cannot free them. You don't know, is there a header available from the memory tracking or not. And we think that this is the reason why NMT native memory tracking is currently only available in Hotspot, but not in the class library. So our approach works with an external hash table, and we store for every allocation. We just store the allocation site and the information of the retrieved memory in this hash table. And when the memory is freed, if we don't find this allocation site in the hash table, that's no problem. And if we find it, we delete it from there. So this is completely transparent to any allocation. And I think it actually doesn't consume really much more memory than native memory tracking, because again, with native memory tracking you have the header, which also adds to your allocation size. The only difference is that with our approach you have to allocate the memory beforehand, but we are using special hash tables which can be expanded or shrunk or grow, so that's not a real problem. And you can also see how much memory the memory statistic is using, so we have a special trace for that. So we have like it uses 4 megabyte is used for the allocation. So we usually we run with 1 gigabyte heap. So I think by default, so 4 megabyte for allocation statistic isn't too much for us. This was for the memory. What other information can we have here? We have, for example, we can print a so-called ASH error file, which you get when a VM crashes. We can get that one at any special time. And actually we have a lot of additional information compared to the OpenJDK ASH error file. Again, recently a lot of information has been added to the ASH error file in the OpenJDK, but there's always this discussion. Let me understand it. The hotspot in the OpenJDK is also running on mobile platforms or embedded platforms where there may be restricted memory restrictions, but as we are typically a server VM, it makes no difference if our ASH error file is 1 megabyte or 10 megabytes. So we dump as much information as possible. So usually we insert there things like the usual thread, the threads, the GC, the loaded libraries, VM arguments. We print all the flags with their values at the time when you get this this ASH error file. So this can be very useful when the customer said he started the VM with special options, but then you can see that actually there are other options active at the moment. So what else do you see? Yes, we have a so-called flight recorder, which is not actually the flight recorder you have in the OpenJDK, but it's just the last events which happened. We have some JIT information like the top memory requirement of functions which were compiled. So you see this function here from the Spring framework, when it was compiled, the compilation needed nearly 100 megabytes, and it took so many. It happened so many seconds ago. Sometimes we observed a very huge memory consumption by the compiler threads, up to several gigabytes, and this can help a lot. So it's good to have this information here available. What other information do we have here? We have, this is the flight recorder. I think this is also available in the OpenJDK. So these are all the VM operations are logged here. So the class loading, compilation, the optimizations, and things like that. We also have a memory region dump. So we dump all the registers and we dump all the memory around the pointers the registers are pointing to. So this is not so useful here when you take a trace, but when a crash happens, this might be quite useful when you have to analyze a crash and the only thing you have is the ASH error file, nothing else. We have also implemented a special memory region called rainy day fund. This is a part of the Java heap which cannot be allocated by usual Java allocations. I told you before that we have an API which allows applications to annotate threads, and for example, all our application servers, they can annotate threads to be system threads, and these are special threads which can use the memory from this rainy day fund, which is just some memory which can be used if the normal user threads run out of memory. The system threads can use the memory in the rainy day fund to recover from this out of memory situation and shut down the virtual machine in a good way, in a nice way. So I don't know what else I wanted to show you here. Let's take.
May I ask you?
Yeah, sure.
Does your tool provide any analytics features or something like advices? Or if you spot any performance degradation, could you just advise increase your bandwidth?
Yeah, sure. But unfortunately, you have to wait. I think half an hour more. I will show this when I show you the profiling tool. So this is actually only logs and traces here. No graphical analysis, but I will come to that in a few minutes. So other things you can do here is you can, as I will show you later, our VM doesn't have to be restarted with a debugging agent. We can switch on debugging at any time. So this can be done from this tool here as well. We can start debugging, stop debugging, or set the debugging port. You can also set trace flags here. So we have a lot of trace flags. I will show you them on the command line, that it will be easier. And clear the output. You can also get things like virtualization information. So this is not virtualized, so you don't see anything. But nowadays, this is quite important, because a lot of customers on any operating system, starting from Linux, Windows, AAX, HQX, Solaris, are running in virtualized environments. And it's very hard for the VM to configure correctly if it gets fake information from the virtualization layer. Like the virtualization layer tells you have, I don't know, 34 CPUs, and in fact you only have a tenth of one CPU, and this happens frequently. And then you say, okay, I have enough CPUs, I start 10 GC threads and 5 compiler threads, and then the VM is actually not doing any user work, because it's stopped by the virtualization. So we have pretty good virtualization detections on all our platforms we run on, and try to adapt the configuration to the virtualization layer. Yes, we have the JIT info I just showed you before. So for every compiler tier, we can get the total time of total compilation time, total bytecodes, total end methods size. We have statistics on the code cache. As I showed you before, we also have information on the biggest compilations we had, and so on. Okay, let's look at the trace flags.
Do you have any statistics for native libraries loaded at runtime?
Yeah, sure, we have that. It's called print DLL info. So you see, these are all the libraries which are loaded in the current VM. So it's running on Windows, so it's all DLLs. Is this what you are asking for?
Yeah, and does it contain any allocation information or some sort of not only the list of loaded DLLs or? You
mean allocation by libraries?
Yeah.
Yeah, we can do an allocation trace. I will show you that when I come to the profiler, and you will see all the. So no, actually, I showed you this before. So it was on the malloc statistics. So okay, I see.
Has it contained?
It has no DLL information here. You're right. Yes. Yeah, probably could add that, but it's not contained now here. Yes, you're right. So. We also have, for example, we have the ARENA statistics. So ARENA is the memory management used by the compiler, and here you see the biggest compilation and how many chunks it used, and so on. I showed you this before. Okay, you can also change the command line flags on the fly if that is useful. So this is not very convenient here. You have to know the option and have to type it in. This is a point where we are working on. But for our trace flags, that's much more convenient. So I think we want to do something the same for the command line options. So these are actually all the trace flags which we are supporting. So we have like trace class loading these tags, trace compiler, trace the GC. We trace file I/O read write, socket I/O. It's really, actually, I think you can trace pretty much everything. Trace spawn, trace OS signals. It's really a lot of stuff. So every time when we have a problem or a bug and we cannot analyze it and we think, well, this would be a feature, it would be nice, we add a new trace, and so this list gets bigger and bigger. Yeah, so let's just have a look at some of these traces. For example, how trace file level basics. It's not here. So if you start to have a Vault program with trace file I/O basics, you will see standard in was opened with file descriptor number, standard error, runtime Java was loaded, hello Vault class, the file descriptor of that, and it's just a basic trace. And if we run it with read write, you get a lot of more information. So you see actually we call the system calls. So every read will be logged. So you see you read so many bytes from runtime jar, and you write so many bytes to standard error and so on. Just two more examples, and then we will come to other things. So we have trace class loading. You get a lot of information. So for example, here you see that a class, for every class you see the class, sorry. For every class you see the class loader, so this was a bootstrap class loader. You see how the class loader was configured, so the URLs, which Java files belong to it, from which file it was loaded, from which thread it was loaded, and so on and so on. Actually, some of these traces are part of the debug version of the hotspot VM, as XX options. Like for example, trace OS MISC. This is available in hotspot if you have a debug build, and we use this information, for example, for a trace. So this is OS MISC trace. It shows you which threads were created, what yellow and what stack size they have, where there's the yellow and the red zone for the stacks, and so on. What we do also print in the SHR file, for example, is the real location of important system calls like malloc, for example, because we had the problem that sometimes we run in environments where users do crazy things like redirect malloc or redirect some system calls because they want to do some fancy things, and then you get a lot of problems. And to see this, we dump all this information in the SHR file or in these traces. So when we analyze a problem, we see, okay, there was a problem in pthread create, but pthread create is actually not the system pthread create from the libc, but it's some wrapper from a user which does some crazy things with pthread. So then user, please solve your problems first and then come back to us. So that's to help us. Okay, we also added, extended a lot of exception messages to show more details. So one thing I want to show you now is our pet store example. I have here, when I press this button, a null pointer exception will be thrown. This was in the SAP JVM, and now let's do the same with the OpenJDK. And when we go now to the console where I have started this, you will see in the OpenJDK there is this thread dump here because of the null pointer exception, and it actually say Java line null pointer exception null. That's it. And we have gone through some efforts to provide more useful information. So we will say now null pointer exception. We're trying to invoke the method so and so, the method add all of a null object returned from pet-clinic get vet list. So if you look at the source code, where I have my Eclipse, no, it's here. Where is the null pointer exception? Sorry, one moment. Yeah, so it's actually this line here, which caused the null pointer exception, and we say that this call vets get vet list. So by trying to invoke the method add all of a null object returned from get vet list. So if you have this line, you instantly know that this method has returned a null pointer, which you don't see if you just see that you have a null pointer exception in this line. So it's just convenience. I mean, of course you can look at all the methods, but it's just nicer that way. And we do some bytecode parsing to do this, because sometimes it's easy. For example, if you have just field access in a line, you could easily say that while accessing field xy of object z, null pointer exception occurred. But if you have such a calling sequence in a line, you really have to parse the bytecode to find out where the null object is coming from. Okay, what else? Yes, we have the example with the no class definition found. What's this? So with the OpenJDK, you get this message, and actually this was improved in Java 6. So we did this already quite some time ago. Before Java 6, you only got this error message. So Java no class definition found. Now they added in Java 6, some added the additional information that there was a problem in the initialization of a class. But we even print some more information. Yeah. So actually we print all the embedded exceptions, and we say no class definition found error, cannot initialize class because freer initialization attempt failed, and you see that there was an area out of bound exception at the initialization of this class, and you also see the line. It's like the class initializer, so static initialization in the class at line 13 failed. Okay, and I have one last example for the extended exception. It's called extended socket exception. So if I run this program here, it's a simple Java program. It just tries to fetch this URL. So from localhost. So I have no web server running on localhost. Oh, this is already the SAP JVM. So the SAP JVM prints the complete say JavaNet connect exception, connection refused, then it say which port and which address. And if you run the same with the OpenJDK, it only say you will only get the information that connection refused, and you don't know what happened. So in big server environments, when you look at the log files, it can be quite useful when you see why you had socket problems, for example. And there is a nice story about this option, because when we actually did this some years ago, we first also printed the name of the host, not only the IP address, and this worked pretty well. So it worked like this. It also printed the port and the address, and it also printed the host name, because it did the reverse lookup. And we actually forgot about this option and didn't know if anybody was using it, but some years later we had some serious problems with the customer, and it turned out that the customer used socket exceptions for control flow, so you shouldn't do that, but they showed a lot of socket exception. But this actually was not the real problem. The real problem was that they had a new security policy, and they only allowed like 5 or 6 reverse lookups in the DNS server, and then they blocked it for 5 minutes. And so when they enabled this, actually everything stood still. And every time we went on the system, first we tried and it worked for several times. And you say, oh, everything's fine. Then after some time it stopped working. And then we remember that we have this nice option. And after that we disabled the reverse lookup, and now you have to switch it on with this extra option called reverse lookup enable. By default it's off now, because it's sometimes you shoot yourself in the foot if you build in too many debugging features. Okay, so I want to come to debugging now and show you how we have implemented debugging on demand. So I have a small program which I want to debug with you. I will just show you the program. It's called debug, and it consists of one function called test. It allocates a double array which gets 3 random doubles, which gets initialized by 3 random doubles, and then we just call square root on these doubles 4 times, and we do a thread sleep, and afterwards we do another square roots and return, and we will call this test function just in a loop. First we call it with sleep 0 to warm it up and compile it fast, and then we call it with sleep 100 so we don't get too much load on the system. So let's run this program now with the OpenJDK. Yeah, so I have a lot of command line options. I can briefly explain you why I use them. Most of them are only necessary to have a nice demo. So actually all what I say you will see it in real life as well. But it's not so easy to demonstrate it without these options, because the VM is very smart and does a lot of things behind your back. So I say xbatch. This means when the JIT compiles a function, the VM will wait until the compilation is finished, so this is synchronous compilation. Then I print every compilation. I switch off tiered compilation, so I only compile on the highest tier. And I only compile my test function, debug test, and the sqrt function which I call. And I also say print opt assembly, so the JIT compiler will print me the assembly it generates. And I also print the inlining information, so I see just to verify that SQRT gets inlined, and trace the optimization. So I see when the VM decides it has to de-optimize a compiled method for whatever reasons. So okay, when you have a look at this, you can see a lot of interesting things. So this is the inlining information. So you see, for example, the SQRT calls, they were inlined and intrinsified. This means that the whole SQRT call is actually collapsed into a single machine instruction on x86. It's just SQRT XMM instruction. Another nice thing which you see is that this method actually does no allocation. So this is the beginning of the method, and the first thing it does, it creates the frame, and then it instantly calls random next. So this is done by escape analysis. So escape analysis detects that the array which we allocate in this function is not escaping our frame, so it knows that it doesn't have to allocate this array on the heap, so it can just allocate the array members on the stack, and of course that's a lot faster. Yeah, then we have this calls to random next, and all the SQRT calls have been inlined. And the only call which remains is the call to thread sleep, and then another SQRT calls, and that's it. So now let's try to debug this with GDB. So if we try to attach with GDB, this won't work, of course, because we haven't loaded an debugging agent. But what we can do, there is a serviceability agent pit attach connector, and we can use this one. For this we have to know the pit of the program, so we call JPS, and so the debug process has 2800. So actually with this agent we can attach. When we look at the VM, we see that nothing has been de-optimized. We can even walk the stack. We say threads. We go to thread 5, our main thread. We say where. We are actually in the sleep method, of course. We go one frame up, so we are now in the test program, and now we can say print locals. No, what do I say? Where are you now? Just locals, sorry, yes, thanks. So, and this may be a surprise. So, it says that the array is null, and D1, D2, D3 are all 0. That's actually not possible from our program, and only the value of D4 seems plausible. So, the debugger pretends to know something, but actually it's not everything is right what he pretends to know. So when we say continue, we will see that the GDB says us that continue is not supported because this is a read-only connection. So this is actually, this serviceability agent connector stops the whole process. It's actually doing the same thing like GDB. So with this connector, you're actually debugging a core file. You have just a piece of memory, the process image, and you can walk the stack, but the information you get is not very accurate. And I can show you why it is not accurate, because we actually stopped at in the thread sleep call, and you can see that at this point the virtual machine at the return of every call, it inserts a so-called save point. So this is a place in the VM where it is safe to stop the VM to do, for example, garbage collection. And at save points, the virtual machine has to know all the live values in order to do garbage collection, for example, but it also has to know the value of all live variables to be able to de-optimize the method. Because it can happen at any time that we get, for example, an uncommon trap or things like that, and we want to recompile a method, and then the compiler it just removes the compiled frame from the stack and creates an interpreter frame where it must assign all the variables which are available. But we see that because we didn't start the VM with a debugging agent, there are no all the local variables are not saved here, because well, actually when we look at the program, we see that after the thread sleep, we only use the value of D4. D1, D2, D3 are not used anymore here. So the compiler is smart enough to just overwrite these values. So the code he generated is he always stores the result of the previous computation in XML 0 and 1 registers. So only the last value is available. So this is here. This is a spill. So before the call, the JIT compiler saves the value of the D4 variable in the stack, and when we called locals from the Java debugger, the VM is smart enough can now find out the value of D4 from this stack location. And this is this is local 8, and at local 8 we have stored this value here. Okay, so now we see that debugging is not working very well with the serviceability agent attached connector. So what we want to do is now we want to do a real debugging session. So we have to start OpenJDK with a debugging agent. So I just stopped the program. So this is the same command line, except that I've added the agent lib option, and start the debugging agent on port 8000. When we now look at the compiled code, we will see that it looks a little different. So one thing that is different is now at the beginning of the function we do a real allocation. So this is actually, maybe it's hard to see, but you can believe me, this is a heap allocation. Heap allocations are actually first done in the thread local allocation buffer, but no difference. You can see here that at this point we do precise class. So this is actually, an array in Java, it's just it's an object, an array, so at the beginning there is a pointer to the class type, and then this is the length field, which is 4, which is at offset 12, and then at offset 16, 24, 32, and 40, we just zero initialize the fields in the array. So when we start the OpenJDK with a debugging agent, it under the hood it switches off escape analysis, because it cannot do escape analysis. It cannot do escape analysis and debugging at the same time. Another thing which we can observe is that now, when we look at the call to thread sleep, we will see that we have now a lot more locals which are alive at this call. So this is actually all the values from D1 to D4. And we see that now the code is more complicated because after every computation, the JIT compiler stores the result of every division and square root in the stack, so they are available later on at the save point. And we can now try to, if this really works as desired. So we now attach with the user socket attach connector on port 8000. We say spend threads. We go to thread 1, which is our main thread. Say where, so we are still in, again in sleep method. We go up one level. We say locals. And now you see that actually we get accurate information. So all the local variables are live and they are available here. And notice that until now, still we haven't de-optimized anything. So this information is available right from the compiled state of the VM when we stopped it. But once we do something like go down again and say step up to return from the sleep call. We are now in our main method, and when we go to another window, we will see that the VM has now de-optimized the test method, and as I told you, all this information here, de-packing thread and so on, all what they say is that the compiled frame was removed from the stack, all the values which are known of the local variables have been transferred into an interpreted frame, and VM will now continue in interpreted mode, so it can single step all the instructions. Okay, so this is how debugging is working in OpenJDK. And now I want to show you how our debugging on demand is working in the SAP JVM. Are you still with me? Okay, so one moment. So this is the same command line, except that now I'm using the SAP JVM and not the OpenJDK, right? Okay, so I start the program. When we take a look at the compiled code, we will see that escape analysis is working. So we do, this is the beginning of the method, we do no allocation here. So we are running actually optimized, but we are keeping the variables live. So we still them to the stack, and before the sleep call, you can see that we still keep the variables live. So how can we now attach to this VM? We have to enable debugging. We can, for example, use our JVM mon tool. As I told you, it's like J command. We have to find our process. It's 2, 4. So. And now I can say start debugging and print debugging information and say that now the VM is listening on port 8000. So please notice that this hasn't triggered any de-optimization or recompilation. It's still the VM has only compiled one method. Actually, the start debugging command only starts the debugging server, so it only starts listening on the socket. All the machinery which is required for debugging is already in place. So and now we connect with JDB. So with usual debugger, Eclipse or what else, we say suspend thread 1 where up locales. So still no the optimization locales. And we get all the locales. Also, we hadn't started JVM with debugging because it's actually SAP JVM installed by default. And if you go back and look at the VM output, we see here not the optimization, but actually this is a message which was printed out because I had the trace the optimization icon, and which only comes in SAP JVM. They say reallocate objects. So actually I showed you that we still run with escape analysis on, but when debugger attaches, or later on when I will show you the memory allocation trace in the profiler, it's the same thing. When somebody really wants to know, then we reallocate objects which have been eliminated by escape analysis on the heap, because actually the debugger is a Java program. It's JVM, and JVM needs an object in order to print it. So we cannot just fake JVM to print an object if it's if it's not available on the heap. So you reallocate objects on the heap, and then you can even assign values to the array. So DA. So it was say DA1. So and you can change the value, and then we say down and step up. And now we're in the test method, and now actually only now. We also de-optimize the method. So this is now the same thing that happened in the OpenJDK, but this de-optimization, it's the usual hotspot de-optimization, and it can now already access the reallocated objects in the heap, which haven't been available before. So to implement this debugging on demand with escape analysis was quite an effort for us. We think we got it right, so it's working, but there's still the rough edges. So every time escape analysis is changing, let's do it another way. JVM offers a lot of functionality, and we're pretty sure that you cover most of it. So if you do usual debugging and Eclipse, it's working pretty stable. But maybe there are still some parts missing. But for now, it's quite good, I would say. So the one thing is we had to fix the escape analysis to work with debugging on demand. The other thing was that we have to keep the locals live. So there is a JVM capability called can access local variables, and this JVM capability can only set at startup, at VM startup. So that's why you have to, with OpenJDK, you have to attach the agent at startup. You can of course load Java agent load later on at runtime, but at that time you cannot change all capabilities. And for example, the can access local variables capability cannot be changed once the VM finish the initialization state.
Are threads processing all debugging features unaided system? Are they available when they're out of memory or some other CPUs?
The thread annotation and system thread has nothing to do with the debugging. So the thing I told you before about rainy day fund and system threads is purely thing about memory allocation. So you can postpone out of memory errors for certain threads but it doesn't interact with debugging, so you can debug system threads like other threads. So actually the system thread is just a thread which has special annotation.
Debug information, there was stop area after reinitialization. Why?
What was there?
Stop area after reinitialization.
I don't think there was a stop. And if there was one, it's empty on x86. So this is actually so-called auto-assembly. This is only a symbolic assembly output of the hotspot, and not the actual assembly. So you can also say print assembly, and you need a hotspot disassembler library, but then you don't get this nice blocking information and annotation, or at least not so much. So that's why I use this one. So where do you see? At the point where we had the memory. But you see it's written here empty encoding. So actually the hotspot puts a store area there, but it's empty on x86.
Yeah, I know. I mean,
Why?
Why? Yes. Why do you need it on internet chat or on other architectures?
I cannot say no. You can ask Vladimir.
Something after allocate, so it's kind of after.
It is at least needed for the default contents of the array to be visible, even if you publish the array to
Yeah, ask what they say afterwards.
Yes, so nominally you have to do this because user can allocate the array, you can pre-zero it or initialize something in it, and then publish the array through the race. And Java language semantics says that you have to observe either default or the stored value state. If you don't have the ubiquitous source stored area after populating the array, you are risking, say, garbage there. So that's, I think, the rationale. Or at least this is the rationale that I see for the bugs that actually expose this kind of.
So I can construct a photoanalysis for views.
But this is not a constructor, this is a static method.
Final fields are different here. I mean, if you just do, say, new byte 10, and you publish that array through the race, what do you expect to see there? JLS says you should see all zeros there, but if you happen to zero memory before through the memory saving operations, you are not actually required to see those default values there. So store provides you that guarantee.
Okay, so of course there is no free lunch. So what we have with our debugging on demand is that we have slightly bigger frames. So if you are running this debugging on demand, we just need extra still slots at any time. And we also have the extra stills which store the values. But as I showed you on our, this was actually the reason why I showed you our benchmark slide. This doesn't impact the runtime for more than about 2 or 3%, so we deem this acceptable, especially because some of our applications or some platforms need really 20 to 30 minutes to start. So even for developers, it's very convenient that they don't have to restart an application server only because they want debug. And of course, it's also very handy when you want to debug a customer system which is running and has a problem at that time, and you want to debug the problem at that time, you don't want to restart it because maybe the problem won't appear anymore. Okay, this was nearly all for debugging. I have one more thing. which is called cloud debugging. Maybe you know that with debugging, debugging is running over JWP, and the JWP protocol is very very chatty. So for if you debug the Eclipse, for example, and stop an application, it does really hundreds of JVM requests to the debugger to get information, to stop all the threads, to get the stack traces, to analyze the local variables. And if you do this on a local system, this is no problem. But if you have ever tried to do this remote in the cloud, you probably didn't have a lot of fun, because with the network licensing, which you naturally have if you debug over a wide area network, this becomes actually unusable. So what we have done is we have inserted a proxy, it's called SAP JVM Headless Debugger, with which you can talk over a proprietary protocol which collects JDWP requests and compresses them and sends them to the headless debugger, and then the headless debugger speaks JDWP with the local debugger. This also saves the problem of unsecure ports, because debugging port is not really secure. If you run in the cloud, usually the system administrator won't open a port in his firewall just for debugging. So with our proxy, we can just tunnel everything through HTTPS or SSH, a secure route, and this becomes possible. So let's see if the demo gods are with us. I'm now in Eclipse, and I have installed our profiling and debugging plugin, which is available from the SAP HANA Cloud platform download site, which will be on the last slide. It's freely available for testing and developing SAP HANA Cloud applications, but of course you can also play around with it and nobody will care. So I will now try to open a debugging session to our pet clinic, which is now running. I have two. I hope at least one will work. So this is now running in the cloud. SAP HANA on demand. It's a demo. It's running somewhere in Europe in the cloud. You see, it's the same application, but it's actually running remotely. And now with the debugger, I can show you the configuration. So this looks something like this. We enter the URL. It's actually the URL of the debugging proxy, which is running in the cloud. And then you enter some credentials and say connect. And it looks like it worked. So you see you are connected now. Yeah, they are connected. I can suspend all the threads now. The threads are suspended. Let's just check it. So if I type home, nothing will happen. It just hangs. So nothing very useful, but just to see that this is really happening. So just go back to the browser and you see we're in the home button. So we are connected now to our cloud pet clinic, and actually the speed is not so bad. So when I suspend it, you see it's like it's looks like we are doing local debugging. Also the application is running in the cloud. So now I enable null pointer exception breakpoints. So breakpoints whenever a null pointer exception will be thrown, and I go back to my application, and yes, I was already here. Yes, and I have to, I suspended the threads. So, okay, sorry for that. Yeah, now we wrote the null pointer exception, and you see the application is hanging, and Eclipse has actually arrived here at the breakpoint, and actually it's here where the breakpoint has been thrown. This was the place I showed you before. We can even look at the exception, null pointer exception, and you see it's running with SAP JVM. That's why it tells you here the nice message that the null object was returned from the get red list call. So we just jump to the get red list, and we see that it actually returns 0. Now let's fix this and see if this is really working with hot code replacement. We save it, and we say resume. We go back to our application. Now again we press the null pointer exception button, and you see we fixed the exception in the cloud, and this was actually a live demo in the SAP HANA Cloud, and it worked. Okay, so this was all for debugging. I don't know how much time is left. Should we do a short break, or I think I have like 30-40 minutes about profiling, which I can tell you, and then we'll make a short break. And
Yeah, let's make a 15-minute break.
okay. Okay, so now let's come to profiling. I will just show you some more assembly at the beginning, but then we will dive into nice graphical analysis of location and GC data at the end. Okay, so I have a little program for profiling. It's nearly the same like before. The only difference is that before the sleep I do square root in a loop to do a little more computation, because now we don't want to debug, we want to profile, so we want to see something. And I start this program. Again, we started with SAP JVM because debugging worked with every debugger, because we support, with our debugging on demand, standard JWP protocol, but profiling, it's actually built into the hotspot, and our SAP profiler is only working with SAP JVM. So the graphical tools are only working with SAP VM. The only strange option, let's start from the beginning. We say X-batch, so we do synchronous compilation. We don't want to use on-stack replacement, no tiered compilation. We say print compilation and print inlining to get full inlining information. And this is a proprietary option. It says time-based sampling enable smooth save point transition. You can simply ignore it for now. I will tell you later what it means.
Is it the longest option?
Yeah.
The longer the better, you know. So. Okay, so I started the program, and this time I didn't use the compile only option. So actually we compile all the methods now, and when you look at the test method, at the inlining information, you see that we have deep inlining now. So actually everything got inlined. We inline the random next double, and next double calls random next and random next calls atomic long get, and atomic long get calls compare and set, and this is all inline. So we have no more calls in our test method, which is good because it's actually what we want. The same happens for SQLT. We already saw that before. Square root is intrinsified, and the only call which remains is our call to thread sleep, because thread sleep is actually a native method and cannot be inlined, and it is compiled here. This end tells us that it's a native method, so actually it's just a native adapter. So from the compiled code we call directly the sleep, but it's still a call. Okay, so now we have not only our graphical analyzer profiler from Eclipse, we can also start and stop all our memory and GC and stack traces from our JVM1 tool. And I will start. We will start with this. So I start JVM1. I attach to our profile. It's 20. This is our profile program. So let's attach it. And now we say start prof. Sorry, I don't have to start JVM1, but JVM prof. So, but the process is still the same. So JVM prof, it's the same like JVM1, but for profiling. So now we start profiling. We say we give him a destination. So we say JVM no profiling save points. I will tell you later what this means. So this is the file where the profiling data will be written to, and now we say start profiling. No, start performance hotspot trace, and we give the option smooth sampling equals false. So this is actually profiling you get from every profiler which is using JVM-TI interface to query the VM or to attach the VM. So what you can see now is that no recompilation happens. So we are profiling the running program, and well, now it's enough. We say stop profiling, and that's it. Okay, now we start a new profile with profiling save points. We write it to a different file, and we say start profiling smooth profiling equals true. One moment, it will get interesting in a moment. True, okay. So what you can see now is that the test method has been recompiled, and it gives this P, which means it has been recompiled for profiling. So what this means, we will see this in a moment. But we recompile the method for profiling to get more accurate information. And now that we gathered enough information, we can stop the profiling. And now we finally use one of our graphics tools. So we can now load this profiling data which we have created into our profiler. I've already done this before. So here is the no profile save point. It was a hotspot performance analysis, and we can now have a look at the hierarchical time distribution. So what you see is we had the total CPU time was 19 seconds, and the profiler thinks that 80.8 seconds we've treated in the sleep call. But we actually know from the program that we always call sleep with 0, so even if it's a native call, there still should be some data which some time assigned to the square root, for example, or to the calls to random. But the problem is, I showed you before that the test method has inlined all the calls. So actually the whole test method doesn't contain any save point, just one single save point at the sleep call. So when we profile through JVM TI, the VM can only stop at save points, and that's where it will allocate all the time, because the whole method, I mean, this is sampling, and every sample will be at the call to sleep. Now, when we are running with our profiling save points, the picture looks a little different. So now we see that the profile also calls random, and it used 1.2 seconds for the call to sleep. We now the profile now only indicates 4 seconds, and the whole test method used like 10 seconds, and we can go to the various lines and see, for example, what happened there. So we have the 4 lines which call the next double with the corresponding times, and we also have other lines which used a lot of CPU time, nearly a second. We can show them in the source. I have to add my Java project to it. Say select all. Okay. Okay, so, and we see in the profiling that we use nearly 1 second in the square root. So this is actually what we've expected to see, because this is where the real work happened. So how did we achieve this? So you can guess it now from what I said, because the so-called profiling save points is when we start to profile a method, we de-optimize the method and recompile it and randomly add more save points at random points in the function, so that we get a more accurate view of the sampling. And after we detach the debugger, the profiler, we recompile the methods again. So you see, after we have stopped the debugging, the method was again recompiled without profiling and runs at full speed, because of course adding more save points not only increases the code, but also has some runtime drawbacks. But again, you only have this during profiling, and it's about 5%, I would say, and we still think that's acceptable if you get more accurate profile information for that. And actually, you can still use the normal JVM TI profiling without additional save points if you want. I can just show you very fast, if you're interested, how the save points look like. I have to start with have to restart the program with print opt assembly, but I think you believe me. So if you want, I can show you this later. Better look at some more features we have in our profiler. So what we can do, for example, is we can use this is now the profiling view of our profiler, and it shows you all the running Java applications, and we can now attach. This is the Tomcat running, and we say we want the allocation analysis. And now actually there is not much allocated, but when I go to my pet clinic, I have prepared a memory leak thread. So let's go back to Eclipse. Actually, I would expect to see something here. One moment, I will just restart. Maybe the problem is that may have gotten I just restart the pet store. The problem is that it's not so easy to write a memory leak because the JIT will optimize it after some time. If you just allocate data without keeping it somewhere, then you don't see it anymore. So we just wait for the pet clinic to reappear. Should be available in a second. Okay, so now you see that now we allocate memory. Boom, boom, boom. Okay, now we stop the analysis. We look at the snapshot. So we can look at the allocated objects. So you see its character arrays, how many bytes, how many objects. You can do a lot of analysis here. For example, again, you can look where they have been allocated. So you see they are all allocated in the leak memory function. If you go to the source code, you will see exactly where they have been allocated. So it's actually here. And what else? Location snapshot. What I showed you before, what I told you before is that we can annotate threads with special text. So for example, you can do an analysis, no, not by thread ID, by user. So you see it's all allocated by Volker. So sometimes this may be bad that everybody sees what you allocate. But I can show you in the code how this looks like. When we go back to the Java perspective, when I create this memory leak thread, I just call this com SAP JVM monitor thread annotation set annotation, and then we have a predefined set of annotations like user or session and so on. And this is actually no public API. We only use it for our application servers so that they can handle this more gracefully. Okay, this was the allocation snapshot. What else can we do? We can do method parameter analysis. This is a very interesting feature. So with method parameter analysis, you can specify that you want to trace a parameter of a method, and all these parameters are saved. You can apply special functions to these parameters, like to string if it's an object, or you can just save them if they are primitive values. And later on, you get a graphical overview sorted by parameter values. So this is very very handy for analysis of, for example, if you have SQL statements in your database, and you trace the SQL statement, and then you get an overview of calls which take a long time and calls which are not so long. And then you see for which parameter your query is long, for example. And you can easily find bottlenecks then, for example, in the database. We can do an example. Let's just start. We go to the VM Explorer, and I restart my example program if it's not running anymore. Okay, so now let's do. We have here the profile, and we say profile method parameter trace. Now we have to specify which parameters we want to trace. So we say profile dot test. We select it, and it has only one parameter. So here we say we want to trace the int, the p1, the int argument. We could also trace the return value. Here you can add modifiers. For example, you can trace the class only, or the hash value, or you can trace a field of an object, or you can even call static methods on every invocation. But this is a private, a primitive type, so we just trace the type itself. Okay, and now we start. And you see we have a lot of method invocations. And we stop the analysis. And now let's look at the results. So actually, I didn't show you the full program before. The test method was the same, but our caller was slightly we call it with different sleep values. This is actually not the right version. So actually this one is the p parameter. Or it should be the p parameter. So when you look, yeah, it was wrong. That's why the call with every parameter took the same time. But I actually wanted to show you that they took a different amount of time. So I just recompile it. Okay, restart it. Do one more method parameter trace. Now we already can choose the same value. somehow didn't work out, sorry. I think I just have to recompile the program. Sorry for that.
Volker, are you sure you use the correct parameter for your sleep in your code? So you think that you switch from 0 to 1, not to...
I switched to 1. Sorry. Yeah, why did you say that? Yeah, sure. I want to use the parameter. You're right. I should use C, actually. Yes, sorry for that. Okay, so we will start one last time. If it doesn't work, we will go to the next example. Okay. I don't know, something is not working. We should see CPU here. Yeah, but now we see it. So if you call it with 10, the elapsed time is 10 times bigger than if you call it with 1. So you can see that for different parameter values you use different time, and then you can find bottlenecks of calling functions with different parameters. So as far as I know, this is a method parameter trace is a quite unique feature. I don't know of any other profiler which supports it. Okay, what other traces we have? Maybe we have file I/O analysis, we have thread dump analysis. So this means that we can write thread dumps at a given interval, and then load, save these thread dumps, and do an automatic analysis. I have saved some of these thread dumps to show you. So we have here, for example, here a thread dump snapshot. So it's 8 thread dumps with interval of 700 seconds, and then we generate a thread dump report. So actually you can access every single thread dump. You see this is an engine running, and you get the full stack of every thread. But what we have done is we have done like an automatic analysis, and this will tell us how much time the threads spend in waiting and in I/O and in running. The screen is a little bit small, unfortunately, so I cannot show you the whole thing. So during this period where we take these thread dumps, there were 10 threads created, 11 finished. We did that much of file I/O, that much of network I/O, and we log the connections, and we can give, for example, hints. So we can see that a single thread consumed 1 hour of CPU time, which is about 60% of the whole system. Then you can open this, and you can see which thread this was. It was this agent heartbeat thread, and then you can just switch to the stack trace of this thread and can analyze why this thread consumed so much time, for example. Another nice feature which we have is memory analysis. It's called, one moment. We have the allocation analysis, which I've showed you, and by the way, the allocation analysis also shows memory allocated on the stack. So if you run the example before, which did escape analysis, you won't see any memory consumption on the heap, but with the allocation analysis, you will still see the allocated memory. And for this to happen, again, we recompile the method, and we don't actually disable escape analysis. We just have a callback, and when we start the allocation analysis, we will just call into the VM and save the amount of allocated bytes to the specific call site. Okay, so let's open some GC history files. This is also a nice feature which we have. So what we do is we save GC snapshots in files. The size is configurable. It's usually 20 megabyte, and there are 3 files, and the data is saved round robin, and usually for the last 3 starts of the VM. So every time a VM starts, it opens one of these 3 files, and then it stores up to 20 megabytes of GC history, and when the file is full, it just starts from the beginning. And of course, it depends on your GC behavior, how much data you can store, but from our experience, like in a 20 megabyte file, we can store data from 90 days, 3 months, up to 6 months, depending on your GC behavior. And then we get this GC snapshot sometimes from our customers. So you can see this is a GC snapshot of a customer. It's run for 81 days, and you see that the overall GC time. So I mean, 81 days is actually a pretty good uptime for a Java application server. And it ran with concurrent mark and sweep, and it had 132 GCs, and this was the 0.3% only we used for GC. And now we can dig into this GC information, and you can actually access every single GC. So you see we had this many full GCs. You can show detailed GC info, and here you can really drill down this information as much as you want. So you get all the statistics of your GC. How many? You also get system information like page faults. Actually everything you want to know about the GC. But you can also get a graphical analysis of this GC history file. It takes some time to compute this. This was a pretty big file, so like I said, it's about 80 days of GC. And but finally, you will get a nice graph, and you can. So these are the GCs. It's a concurrent GC, full GC, you can zoom in. You can get overview of the heap. So this is used bytes in young GC, used bytes in old GC. You see the typical graphs for GC allocation. You see here bytes promoted, but you can also at any time create your own graphs. Graphical analysis, custom selection. So you can select all these attributes. Actually, a lot of them, and I mean I just select some here, and then you will get a graph of the selected attributes for the whole period where this GC data was collected. So I don't know. I think we run pretty much out of time. I could still show you some other features, or I could show you how the location trace works with escape analysis, but I think we can also let it for next time. So
Up to you.
So are there any questions so far for the second part?
What about native libraries? From the first
For example, SAP JVM.
Can we have some memory allocation? Can we profile some memory allocations by native libraries loaded at runtime by the application?
You mean
by system load library?
Yeah. So you mean like native memory allocations?
Yes.
Actually, I don't think we can, but I can ask my colleagues. They can take it as feedback. So I think we only have the
separately by libraries.
I mean, of course you cannot trace it if you have like native libraries which don't come with the SAP JVM, then they are not instrumented. So if they directly call the system allocator like malloc, we don't trace that. But you would have to redirect malloc for all the loaded libraries. We don't do that. You would have to wrap all the allocation routines, which would be possible, but we don't do it.
Do you provide any libraries for malloc redefining?
No, we only wrap malloc for allocations which happen in the JDK, and we don't redirect the system malloc. So other libraries can still use system malloc without us knowing it.
And do you have any profiling some, I don't know what's called, operations to exclude CPU weight on monitors? So
we can exclude sleeping threads if that would help you. I think if we
the
do
sleeping time, to figure out the time that that was really eaten by processes to optimize our algos.
I'm not sure if this is what you want, but you have this option here, so you can include or exclude sleeping times. So if I run my example with profile where I did sleep, if I exclude sleeping times, then you won't see anything. Also, you can in performance analysis, you could this was the method parameter location. You can say here,
Not this one, but the other profiling.
which other profiling? The hotspot and that?
With the SQRT method.
Okay. I cannot find it anymore, but what I wanted to show you is that you can show, you can actually exclude the sleep time here somewhere. I only don't. You can show here also compiled versus interpreted time, native versus non-native, and somewhere there is an option to exclude sleep times, but I don't find it now. Maybe it's already.
And will it be excluded from the countings, time countings on the right?
I think we count everything, but then you can exclude it in the graphs.
And will it be excluded in the digits?
Yes,
Oh.
I think yes.
And what about native I/O, like socket read? Is it counted as CPU time or not? So, because regular profiles show these threads as consuming CPU, but in fact they are not.
Actually, I cannot say it. I have to ask my colleagues. So, but I would be happy to ask and to follow up on this question. But you mean waiting on I/O?
Yes.
I'm not sure. So, I have to ask. I'm not a profiling expert.
Any questions, guys?
Okay, thank you, Volker.
Okay.